So why do we want to take a look at the Hydras? So Hydras play a central role in content discovery as, well, they claim to play a central role. Let's take a look at the stats later on. And yeah, several users and applications depend on them. They make up a significant proportion of the whole network nodes that are DHT server nodes. And as far as I know, there's no thorough investigation so far of the Hydras' performance and how much they actually impact the performance. And also, Yannis earlier shared this, our paper that we published and the reviewer feedback. The main concern or the biggest negative point was that we didn't take a look into the content locality. So we took a look at where DHT nodes are geographically located, but not where content is. And our thought is that we can take the Hydra database to actually find out where content is stored geographically. So for the talk, we will briefly cover what Hydras are. Then we'll take a look at Hydras in production, so how they are deployed at Protocol Labs. I will share a couple of Grafana panels and Grafana dashboards, and we will take a look at the stats there. Then I will describe our measurement setup, so how do we find out where content is stored and what else can we do with that data. And then I will share a lot of graphs, so it's going to be fun. So briefly, what are Hydra boosters? Mikkel already touched briefly on that, just to recap. And I got from their GitHub page this brief paragraph at the top. So Hydra boosters are a Hydra with one belly full of records and many heads to tell other nodes about them, charged with rocket boosters to transport other nodes to their destination faster. And basically, Hydras are just a new type of DHT server node that are basically running a Sybil attack on the whole network and distributing themselves across the whole key space so that every query that you issue to the DHT will eventually come by one of these Hydra heads that you can see here. They have three main activities. So they receive add provider requests from the IPFS network, store them in one big database, and so that other heads of that Hydra can directly access the database and serve it right away, although they may be far away in the XOR key space. And then they use those provider records to answer GET providers queries from other IPFS nodes. And also, if they don't know about a provider record or they don't know about a CID, they proactively search for those provider records in the network to store them in their own database. The code is open source. You can find it on the right on libp/Hydra boosters. So this is just briefly what they are. So Hydras in production, how are they run at Protocol Labs? Right now there are around 2,000 Hydra heads distributed across, I don't know, probably 135 Hydras. So each Hydra has a couple of heads, and they are then horizontally scaled. So they are run on ECS on AWS with Fargate, and all those Hydra instances are backed by a DynamoDB. And this means, since the Hydras are distributed across the whole key space, and every add provider RPC ends up at a Hydra head, at least in theory, that the Hydras should know of all provider records that are stored in the DHT, which would give us a good view into the IPFS network here. But let's continue with Hydras in production at Protocol Labs. They receive tons of requests. So on the x-axis, you can see the time, and on the y-axis, you see the received requests per second. The blue line are the add provider RPCs, and they wobble around 50,000 requests per second. The yellow line is the find node RPC, so this accelerates the the peer discovery, which wobbles around 15,000 requests per second. And also the one other very active RPC here is the get providers RPC, which is also around 15,000 requests per second. So in total, they serve, or they receive requests for 50, 60, maybe 80,000 requests per second. On the other hand, they also send requests. So I said they proactively search for provider records that are in the network, that they don't know about and receive a request for. And this is also in the order of a couple of 10,000 requests per second that they send out. So they are used quite a lot, and they handle a lot of traffic in the network, in my opinion. For the total provider records that they store, so as you've also heard from Mikkel, they have a TTL of 24 hours. So there's an up and down going on. On the x-axis, again, time. On the y-axis, this reaches from 1 billion at the lower left to 5.5 billion on the top left. So that's the order of magnitude that we operate with regards to provider records in the network. And yeah, you can see that there's an up and down. So provider records come and go depending on, actually I don't know what this depends on, so probably just activity in the network. Total IPNS records, that's a fun one. So the bottom left starts at around 1.6 million, and the top left stops at 1.9 million, and you can see that's a straight line going up. This is just because the Hydras don't prune any IPNS records, so we have all the IPNS records since, I don't know, March or so, and so they just don't expire. So this is, it's hard to tell how many active IPNS records are there actually currently in the network. So, but I mean, we're in the measurement track, and if anyone wants to do an analysis on that, I just want to point out that this data is there, and we could collaborate on that. This is a tricky one. These are the provider prefetches. So I repeat myself again. The Hydras go ahead and search for CIDs in the network that they don't know about. And there are a couple of different cases that we need to consider here. So you can see the orange line at the top. This is the case that the Hydras have received a record, a CID that they should serve, but they didn't have it in their database. But then they went ahead and searched in the network for the CID and actually found a provider record. So this is the thin orange line at the top. Then the blue bar there is the basically the successful requests from for Hydra for these Hydra provider records from Hydra peers. This means I request something, a CID from the Hydra, and they could serve it right away from a cache. Then the yellow bar here, the biggest part, is that the Hydra ran into so-called negative cache. This means the CID was requested previously. The Hydra went ahead, tried to find it in the network, but has not found it, and thus has put the CID into a negative cache. That means if another peer comes across, if another peer requests the same CID, the Hydra knows, well, I just searched for it, I couldn't find it, well, I just discard this CID. And the green one at the bottom is the Hydra went ahead, tried to find it in the network, and couldn't find it in this particular time slot here. All right, so these are just some metrics of Hydras in production at Protocol Labs. Our measurement setup. So what do we want to do with that data? So the Hydras sit on a lot of data in this big DynamoDB database. And we want to know, do Hydras really cover the whole hash space? So I said they distribute themselves in the whole key space in a very specific order, uniformly, so that every request should end up at least one Hydra head. But is this actually the case? We want to find out. Then, again, from this reviewer feedback, where is content stored geographically? So is it in the US, in Europe, or in China? We don't know yet. And then also, what's the content churn? So if I provide a CID, what's the percentage of CIDs that are reprovided? Or how long do CIDs stay in the network until they just churn away? And most importantly, do Hydras really speed up content routing? I mean, Mikkel already had given a brief glimpse into that this may not be the case, but we'll see. So this is the data processing pipeline. I think I will just skip over that because this will change a lot. But maybe for the sake of completeness, there's this DynamoDB that you can see here, and we're doing like point-in-time recovery every 24 hours into an S3 bucket, and then we run a couple of Spark jobs with AWS Glue, and then query the data with Athena. And yeah, we have the whole tool belt of SQL queries attached to us, so that's great. Each DynamoDB dump is around 200 gigabytes, and if we also want to have the peer records, which we want to have, this is another 1.5 gigabytes. So this is the size of the data that we are operating with. And if we are doing these DynamoDB dumps quite frequently, this adds up quite fast to a lot of data and makes it difficult to handle. Just for everyone to know which kind of data we have. So if you need this data at some point for one of your studies, provider records, as you may know, consist of the CID, then the time to live, and then the peer ID. And the peer records consist of, for us, most importantly, the peer ID and then the network addresses. And since the Hydras know of all the provider records and thus also know of all the peer records, we can basically join both of these, let's call them tables with these different columns together based on the peer ID, and thus associate a CID with a network address and then this network address to a geolocation. And so there's this complete link. So we have a CID to a geolocation. And we did this. And yeah, let's get to, here we joined those two columns together. All right, what are the results? First of all, the hash space coverage. On the right-hand side, you can see the straight line just indicates that we have a very uniform distribution of peer IDs, so this is good. But also, we wanted to know how often a Hydra head appears in the proximity of 20 closest peers. So what did we do? We took a full network crawl, and so the snapshot that we also talked about previously. Then we put all the peer IDs in this binary trie, which is the representation for this XOR key space, thanks to Guillaume, who built this brilliant library here. And then for all the peer IDs that we found in the network, we calculated the 20 closest peers according to the XOR distance. And we checked, well, is a Hydra head in there or not? And we found out for the 16,200 peers that we found in the network, this is the case for 15,700, which makes around 97% coverage of the whole hash space, which is good, which is the intention, and also we just confirmed it empirically, basically. Then, let's start with the peer IDs, since all the Hydras also know, besides all provider records, everything about peer records. We were able to map the peer IDs according to their network addresses to different locations, but sometimes some peers advertise multiple IP addresses that can be associated to different countries. So I could advertise an IP address just that maps to, I don't know, the US, and another one that maps to France or so. But this is the minority. This is just a verification here, or like a sanity check, basically. Most of the time, like 95% of the peers just advertise peer addresses that can be associated to one country. And we will only focus on this big bar in the next slides. And this is the peer ID distribution. So most of the peers that actually provide content sit in the US. This is around, I don't know, 45, maybe roughly almost 50% of the peers. And then we have a steep drop, and the next country there is Korea, and then China, Germany, Great Britain, and so on. So the most of the peer IDs that we find in the network, according to the Hydras, live in the US. Then the CID distribution. So this is something that we also talked about, that someone asked me yesterday. So how many providers do CIDs have on average? And here we can see that. So we know, here we can see that around 85% of CIDs only have a single peer ID as the provider, and then 10% have two providers, and 5% around 3 providers, and so on. So the vast majority, again, is just provided by a single peer ID on a single machine, which may be good or not. Probably would be better if they were distributed. And then we can go ahead and associate, as I said, the CID with their countries. And this is a little bit more ambiguous, as you can see. So most of the CIDs, again, can be associated to one country, but then there are some CIDs that can be associated to multiple countries. And in the future, so in the coming slides, again, we will focus only on this big bar on the left, so the ones where we have an unambiguous association to a country. And this is the distribution we wanted to have. So this means that this just shows on the left, so the y-axis here is the percentage of all CIDs and that are associated to the country that you can see at the bottom. And you can see on the left, the vast majority, again, is provided from the US. Like 55% of all distinct CIDs that we find in the network are, have a provider that sit in the US. And then the second the second prominent one is the Netherlands, and then France and Germany. And this is actually what we wanted to find out. Then we can also check how many CIDs there are per day, and you can see on the y-axis again, this goes from 0 to 1 billion. So the blue bars show the number of distinct CIDs at one particular point in time, and this shows we have 1 billion CIDs, or content chunks if you want, and if you multiply this with the with the chunk size, we end up at around 120 terabytes of data, which is just an approximation, but still, this is the amount of data that would be addressable through the DHT. So just to have a ballpark there as well. And then what we did is we compared the number of distinct CIDs with the previous day. This is the orange bar there. And as you can see, this is almost half then, it's only around 50% of the blue bars there. And this means that 50% of all CIDs leave the network within 24 hours, but also 50% of new CIDs join the network. So there's a pretty high churn of CIDs. Which is, well, for me was quite unexpected. So this means that there's either an application that produces a lot of ephemeral content, or there's something inherently, some inherent property to the network that makes this property apparent in these graphs here. And then the green graph here is again the intersection of the second previous day, which is slightly less than the orange bars, but not as pronounced as the previous drop. And this is kind of the CID churn that you can see there, that we also wanted to know. And what we can do now is also check the top providers. And this is quite concerning, I would argue. Here we can see on the x-axis different peer IDs that I have truncated. And on the y-axis, the percentage of total unique CIDs that they provide. And we can see that a single peer, a single provider, provides around 13% of all CIDs in the network. And then it drops to 9%, 7%, and so on and so forth. And if we add up the top 10 peers here and their percentages, they make up over 50% of all CIDs provided in the network. And if we look at them a little closer, so some top providers, forensics here, these are again the ranks and then the PRDs and so on and so forth. We can see that many of them I was able to map to web3.storage, but then there are a couple of ones that I'm not sure where they belong to, so we could do another forensic session and find out who they are. And yeah, this is just 50% of all peers, of all provider records are provided by these peers there. So probably some centralization concern, perhaps. Let's discuss this. All right, and the last question that we have: do the Hydras actually speed up the latency, so the content routing and providing, content routing in the sense of providing content to the network and also requesting content from the network? And the top graph shows some CDFs that I will go into detail in a second without Hydras. So I did the same that Mikkel also did with his experiment. I just disabled all the Hydras from the... So if I want to request something from a Hydra, I just drop the request and do something else. And at the bottom we see the same experiment, but we also use Hydras for that. And this is the box with this red box that you can see there shows the CDF of the DHT walk, which the Hydras supposedly should speed up. And this is a little hard to compare, so let's have a look at that a little differently. Here we can see on the x-axis the different regions that we probed the network from, and on the y-axis the latency, so the lookup latencies. And we can see that Hydras indeed speed up content routing, but only slightly. So the blue bars here are the content retrievals with Hydras, and the orange bars are the content retrievals without Hydras. And even so, for the Middle Eastern node here, can you see my? Yeah, it even dropped. So the network seems to have been more performant without the Hydras, which is unexpected. And this may indicate that this is just a statistical, well, it's quite consistent, but it could also be some noise in the measurement here only. So from this study, we could conclude that the Hydras actually don't really speed up the DHT lookup process as it's intended. All right, and that's it. Just once again, I'm also running this net hole punching campaign. Sign up and join our measurement campaign, and I will just leave this up for questions, and this is my brief talk about the Hydras. Thank you.
Cool, questions?
Thanks, Dennis, for the amazing work again. Apart from Nebula Crawler, anyway. So I have a bunch of questions. So first but I'll ask maybe a couple of them. So one on the negative cache versus not appearing. I mean, you were explaining about the data set in the beginning where you had like 4 different chunks, right?
Right, you mean this graph?
Yeah, exactly. So the major portion you mentioned is a negative cache.
Right.
So I want to understand what's the difference between the negative cache and what's like, when you say like CID not found, like there are 2 things there, right? So I just,
Right, so you mean between the green one at the bottom or?
Exactly.
Yeah, right, so but for the green one, the Hydras actually went ahead and tried to find it, but couldn't find it. For the yellow one, the Hydras, just didn't even try because they tried previously. And for, again, the blue ones, they had it.
Yeah. Okay, that part is clear. Okay. So one is a subset of others. So, I mean.
Yeah, exactly. Sorry. Maybe that was unclear, yeah.
Okay, cool. And on the graph where you explained with multiple dates and the commonality between common CIDs you found on the previous day, this one. So if I see between 21 and 22, I see an increase in number of common CIDs, right?
Right.
But how is this possible? I mean, if you take an intersection between the total number and the number that was appearing on the previous day, I assume this is a unique CID count.
So this is so you mean the orange bars?
Orange bar, yeah.
The orange bars are always only the intersection with the previous day. Does it make sense? So I take the blue bar of one day and intersect it with the blue bar of the previous day, and then the intersection is just the number of peers is just the intersection.
Okay.
So it's not like
the blue bar and the orange bar. Okay.
Yeah.
Okay, makes sense. Okay. And did you see any anomalies like use of VPN or
use of what?
VPN or peer IP rotation, those sort of things?
No, I have not. The only anomaly is that there's like such a concentration with just a few providers. But no, sorry.
Okay.
Well, sorry. It's good, I think.
So one last question on the Hydra measurements. So one thing is you have done the experiments on the AWS, I think.
Yeah.
So do you think having these nodes centrally within AWS might say that Hydra is not performing better? If you had, like, let's say, the node at the edge or the user node, maybe the Hydra's effect might be a bit more clear, like whether the routing has better performance or not.
So you mean if we deployed Hydras closer to the users, or what do you mean?
No, I mean to say your experiments, if you run it closer to the user and not on the AWS.
You mean these lookup experiments, or what do you mean?
The last graph,
this part?
No, I mean this one and the next one.
That one?
This one. So if you run it instead of on AWS, if you run it on user nodes, because Hydras, I think, are deployed on AWS as well.
Right.
And this is sort of a best case scenario, right?
Yeah. Yeah, that would be a good study to do, to run it closer, like not at the backbone of the internet, basically, yeah. This was also a review of feedback, but we haven't touched that one yet. But yeah, good point, definitely. This would be more realistic for the end users, I believe, yeah.
Cool, thank you. I'll ask other questions offline.
Yeah, cool.
Thanks for the talk.
Yeah.
The top provider graph that you showed, do you take into account, because I couldn't read the y-axis, do you take into account just the sheer number of CIDs, or do you take into account the popularity, so the number of requests that you get per CID?
This is just the number of CIDs. So let me just briefly read out what it says at the top. So it says the percentages can add up to over 100% because single CIDs can be provided by multiple peers. And this could be, so imagine there's only one CID in the whole network and provided by two peers. Both would provide 100% of all CIDs, which would add up to 200%.
Right, yes, but I mean, so if there is like a CID that is requested a lot and the other one that is not popular, they will count as one for their peers.
Yes.
Okay. Have you checked also taking into account the popularity, just if the distribution kind of changes?
Sorry, say that again. So the number of the popularity.
So if you kind of multiply the CID by the number of requests you get for the CID, you can kind of get, one CID can be worth more or less depending on its popularity. Whether the distribution will be the same. Have you run this kind of experiment or not?
I don't think I get the questions quite.
Okay, we can take it offline.
Let's put it offline. Sorry.
I had one more question about this region graph that you showed at the beginning.
Which one? Sorry.
This with yellow, blue, red. So you have a lot of the yellow and the green regions are significant. Do you know what kind of CIDs are those? Were there CIDs that used to be in the network but disappeared, or they will become available, or you didn't check that?
I have not checked that. Would be interesting to see which CIDs I actually provided and requested and then couldn't be found. But we haven't looked into that. But it's super interesting to do, definitely. Yeah.
Okay. Thank you.
Hi.
Hi.
The slide at the end shows that the DHT lookup in using Hydra takes about 4 seconds.
That one?
The one next to it.
That's easier to see here. It basically it's just the same, but yeah.
Yeah, so it takes about 3 to 4 seconds to look up in Hydra.
This is the 50th percentile, though. Yeah, but yeah, you're right.
Okay, so it's even worse than the 90th and 99th.
Yeah, I have those in the backups here. So this is the 90th percentile.
Okay.
And then also the 95th. Maybe that's probably more representative what you experience from the network then. Yeah,
so do you have a breakdown of where this latency is coming from? Maybe I'm misunderstanding how Hydra works, but whenever there's a hit, it will just query from DynamoDB and get back to the user, right?
Yep, that's how they would work, yeah. And so I have not taken a deeper look at why the Hydras don't speed up the network so much, but the breakdown basically is on this graph, which I just skimmed over. So you have the DHT walk, and then also the content fetch duration on the right-hand side, and also in this DHT walk there are a couple of steps that are performed that we could also dissect to dig deeper into that. But yeah, we have not done that in such detail to really know why the Hydras don't speed up the network as expected.
So the 4 seconds in the 50th percentile, including fetching the data?
This one here. Honestly, I don't know because I didn't create this graph, but I would assume this would include the content fetch as well. Yeah, because I mean, if we know from the beginning that the lookup actually takes, let's say, 10% of the whole time, then we should not expect that the Hydra would actually help more than just 10%. True. Yeah. So yeah, I would need to look up which part of the content retrieval this actually depicts, but.
Yeah, if I remember correctly, that's the whole thing. That's why in the Middle East there is, the without Hydras is faster, because it doesn't really make sense otherwise. There must be something, with the bit swap before and the content fetching after. So that's for the whole thing. It's not for the DHT only, I think.
Yeah, I also think this should be the whole thing. Yeah.
Thanks for the answer. Another question, so Hydra, is it a global service or is it regional?
Anyone could run a Hydra, and Protocol Labs is just running not even one big Hydra, but as I said, 2,000 heads across 130 or so Hydras. And so you could argue it's a global service to the network, or a single point of service. But yeah, how much service does it actually give to us? I don't know. yeah, so, or what do you mean with global service?
At least let's say the DynamoDB table in the test cases here in the Middle East. Is the DynamoDB table hosted in the US?
Sorry, yeah. So, you mean if it's distributed across the globe? So this is just run in US West 2, I think, on AWS. So just there.
I see. Okay. Thank you.
Yeah. All right.
Question?
East? Okay, sorry. It's US. US East 2. Yeah. Here we go.
So, given that they are not affecting content speed that much, why are we keeping them online?
Yeah, we already heard today that there's some ideas of just turning them off and watch the world burn. So
Yeah, that's a kind of precursor experiment to see if it's a safe choice to do, or then having a next part to the experiment which is going to be more real, and just turning them off perhaps gradually, and then eventually have run some days without it to see if this persists or not.
So if I understand right, the intention of the prefetching is to find CIDs that are hard to find in the network, right? Do you have a sense of how good of a job it's doing? How much is it making it easier for other peers in the network to find hard to find CIDs?
Sorry, what do you mean? What does the prefetching do there?
So it's going to search for CIDs that it doesn't know about, right? And then
Right.
it will cache them, which improves the availability or like the knowledge of that CID in the DHT, right? Like, is that helping other peers find content that otherwise is like hard to find?
I mean, in theory, I would say so, but as we can see on this graph, this barely happens. It's just the orange strip at the top when this actually works. So this orange strip there says, I requested something from the Hydras. The Hydras didn't know about it. The Hydras went ahead, fetched it from the network, and then saved it for others to serve it to others then. But this is only almost negligible to the rest of the requests, right?
Well, the impact of them doing that would show up in the blue section, right?
Sorry?
Means, like if they were successful doing that, then subsequent requests would show up in the blue, right?
Yes.
Okay.
Yes. Yes. Mm-hmm.
Okay.
Yeah, so this is basically, the orange one is showing how many are the, say, one-timers perhaps, in caching kind of terminology is how many users, are asking for a piece of content just once and never again. So it doesn't make sense to cache it anyway.
Right.
So I guess that's what it is. So it would be interesting to see, okay, the Hydras are fetching this. How many more peers ask for that after?
Yeah.
To see if it's worth the effort.
Yeah, exactly. Yeah.
Probably if we can see if a gateway and Hydra can talk to each other and cache it based on like gateway policies,
right.
It might be better because we know that gateways are quite good at caching, right? Is it possible, do you think?
They are not connected with gateways, but I know that they are working together with indexers somehow, but I don't really know more about that. Maybe Gus may know? I don't know. No, okay.
Cool.